So take a minute and get organized for the day. All of your materials out. I don't know if you really need a formula sheet out, but we might be referring to it a bit today. Phones away, calculators out, something to write with. And I'm going to go through a quick review of the Compton effect. I posted the review package to Google Classroom. I don't know if any of you looked at it, but I posted it and then I posted a key and said, well, I only went through it once, so I have to check the key. And so I started checking the key, and I was very discouraged when I got answer 1 wrong. But it turns out I think there were 3 or 4 errors in the key. They are corrected now. And I have a print copy of that I will give you today. But your exam is Thursday of this week. So tomorrow, again, expect a little quiz on the photoelectric effect, calculation-based quiz. Today we're going to cover something called the de Broglie wavelength, and then we're going to be reviewing tomorrow and Wednesday. The traditional handout that I give you that has all of the content, you will get that today. But like the last unit, I am not going to, not waste, it would not be a waste, but I'm not going to spend a class time tomorrow going through this. I have a video I can link to in Google Classroom that goes through all of this content. That would probably be about 45 minutes to an hour, and I think it would be an hour well spent. Okay, I really do. I don't know that I'm going to have time to make one this semester for this unit, but I definitely have one from last semester, so the handout might be slightly different in places, but the content is going to be the same. Okay, so your exam is Thursday, bottom line. Compton scattering. Compton scattering occurs when photons are scattered by free electrons in a collision. The electrons must be free. If the electrons are not free, the electrons instead are bound to an atom, then you're not talking about the Compton effect, you're talking about the photoelectric effect. The other difference is normally, so there's no work function here, normally with the Compton effect you're usually talking about X-ray photons, whereas the photoelectric effect you're talking about ultraviolet at best in terms of energy. You probably don't go past ultraviolet photons for the photoelectric effect. The photoelectric effect can also occur with infrared light. I've never seen a situation that has maybe microwaves or radio waves causing the photoelectric effect, but definitely there are some metals where infrared will. Pulling myself or steering myself back on topic to the Compton effect, during the collision of the free electron and the photon, the free electron, by the way, is at rest to begin with. Energy is transferred from the photon to the electron, and this is the fundamental difference between this and the photoelectric effect. The photon is not absorbed. It simply glances off of the electron, and the photon loses some of its energy. Compton had developed a formula for the momentum of a photon. I'll show it to you officially in a second, but the formula is the momentum of a photon has a magnitude of Planck's constant over the wavelength. During the collision, momentum and energy are conserved, and there's this Compton scattering formula. Okay. So this is what it's looking like pictorially. Notice I've really exaggerated things here, that the wavelength of the scattered X-rays is longer than the wavelength of the incident. Even after doing a couple of examples, we saw that the wavelength difference is very tiny. It's almost imperceptible. If I were to draw it to scale, you wouldn't notice it. The final wavelength is always equal to the Compton shift, the delta lambda plus the initial wavelength. Once again, both energy and momentum are conserved, but if you had a choice and you were going to analyze one of these, don't use conservation of momentum, because momentum is a vector, and then you got to deal with two-dimensional collisions. It's complicated. It's more work. This is probably what you would use in most analyses of the Compton effect, that the energy before is equal to the energy after. So the photon energy before is more than the photon energy after, because the photon lost some of its energy to the electron. Okay. I'm just pointing out here that you can build an equation, but this is nothing you need to write down. Energy of a photon is hc over lambda. Energy of an electron is 1/2 mv squared, so you can build this formula. And you can certainly write it down if you want, but you don't have to. It's just, it's taking this is what we talk about when we say students in high school physics will be more successful if they understand the principles as opposed to memorizing formulas. I certainly wouldn't set out to memorize this. I would set out to know this, what's in black. So we have these formulas, right? The two energy formulas for photons, the formula that combines energy and momentum, and then I also have this momentum formula for photons, and then we have the traditional formulas for energy and momentum here. You might wonder why this P equals H over lambda is separate from the other three. We'll get to that later today. So does anybody have any questions? Oh, and I should change my notes. In fact, I've got it on my list of things to do. In question 4, a helium nucleus is an alpha particle. Just so you know. And certainly by the end of the year, you will know why it's an alpha particle. But the bottom line is if you're going to use this formula, does yours say helium nucleus, or did I change it already to alpha particle? It says helium nucleus? Okay. When you calculate the wavelength shift of the photon, you have to use the mass of a helium nucleus because it's the thing that's scattered. And I should have told you that before. I would never give you a Compton scattering problem unless it was a photon with an electron, even on an exam. I suspect that the diploma exam, in 99.999% of the time there's a Compton problem, it will be an electron. But I could see them giving you something, some other particle at one point. You never know. Those guys are tricky. Devious. Anyway, does anybody have any questions you'd like me to go over? Go ahead. This one. Okay. So, as I said to you this morning in Sabre Support, if you were here, this was the conversation Armand and I had. In this situation where you were told the wavelength of the photon before and the angle that it scatters at, and let's be clear here, the angle is 180 degrees because it goes straight back. So to go from heading north to heading south requires a change in direction of 180 degrees. I can ask you Compton effect questions that ask you to determine the wavelength shift. Now, when I explained this morning to you, Armand, we did the whole thing, and then I said you could do this, this, this. But one of the things I could expect you to be able to do is find that. And I would say that's among the easiest Compton effect question. But then I can ask you, instead of asking you that, I can ask you this, everybody, lambda f. But if you find the wavelength shift, you can find the final wavelength by adding the initial. Okay. Instead of asking you for the wavelength shift, I could ask you for the final wavelength. Instead of asking you for either of those, I could ask for the energy of the photon afterwards, which is a typical kind of question. But to find the energy of the photon after, you need to know the wavelength after, which means you need to know you need to be able to calculate the wavelength shift. So do you see what's going on here? That anything at the bottom of the list requires that you calculate everything above it. I could ask you to calculate the kinetic energy of the electron. I'm not going to put a subscript of electron because kinetic means it has mass. I could ask you to find this. But the only way in this kind of question you can find the energy of the electron is to find the change in energy of the photon. Right? So at this point in time, you would be saying, well, the energy of the photon after minus the energy of the photon before is the kinetic energy of the electron. So if I asked you, I know this is getting repetitive, but if I asked you for the kinetic energy of the electron after, you would say, well, I need to know both of these energies. And by the way, we know the wavelength before. So do I have enough information to find the energy of the photon before? Yes. Do I have enough energy to find the energy of the photon after? No, because I don't know its wavelength after. But then I can find the change in wavelength and add it to the initial to find the final wavelength, to find the final energy, so that I could subtract them to find the energy of the electron. Or, and this is the penultimate question, I could say, instead of asking you any of that, how fast is the electron traveling afterwards? Now, this is the ultimate question, except it's not an electron, it's an alpha particle. So let me make that little correction in my notation. So here's what we have to do. We need to calculate the wavelength shift using this formula. We need to find the wavelength shift using the Compton shift formula so that we can add that to the initial wavelength, so that we can know the final wavelength, so that we can calculate the energy of the photon before and the energy of the photon after, so we can subtract the two energies so that we can set it equal to a half mv squared to find V. That's exhausting just thinking about it. And you know, I'll be honest with you. I doubt very much on an exam I would give you a question that asked you for the speed. I might. The reason why we're practicing this is if you can find the speed, you can find anything else that I might ask. Anything. So I'm going to do this on my calculator. Okay? And along the way, I'm going to be using formulas for the energy of a photon. So, first of all, what is the wavelength shift? It's Planck's constant divided by mc, which is 6.65 times 10 to the negative 27, because it's not an electron, and also divided by the speed of light, and multiplying by 1 minus cosine of 180, double checking my mode, and double checking all of my numbers. And I'm pretty sure they're right. The alpha particle mass is right, 6.65 times 10 to the negative 27. I just, you know, it's nice to check that because we don't use it that often lately. So this is what I'm getting for the wavelength shift. Very tiny wavelength shift. I'm going to add that now to the initial wavelength. So if ever there's a question in this course that requires focus and organization and carefulness, it's here, right? So now I'm adding the initial wavelength. This is the final wavelength. So now I need to go hc over lambda of that. I've got these backwards, these two energies, because there's more energy before. And I paused there, I screeched to a halt intellectually because I thought I'm going to get a negative. What's going on? I'm subtracting the wrong way. So this is initial and this is final. The reason for that, I just want to go back to this. The reason for that is this statement, right? The law of conservation of momentum says, or energy says, initial equals final, so we have to subtract the final photon energy to get the leftover, which is the electron. Okay, so I need to take now hc over lambda, 6.63 times 10 to the negative 34 times the speed of light divided by the initial wavelength, and I need to subtract. I think we're in deep enough here that I don't think you need to hit equals and write down all of these energies. hc over lambda minus hc over the new lambda, which is currently the answer on my formula sheet, not my formula sheet, on my calculator. So hc over lambda minus hc over lambda gives me this energy, and this is the change in energy of the photon, which is the energy of the alpha particle, of the scattered particle. So now we set that equal to a half mv squared, and finding that calculation, v from the energy is, one of these semesters I'll keep track, but we got to be in the hundreds of, 100 times we've done it so far, somewhere along the way. So I'm going to multiply this by 2, I'm going to divide by the mass, and then I'm going to take the square root and get 2 times 10 to the 4 meters per second, which is correct. So this is, as I said, the kind of penultimate question. And then, to poke you with a sharp stick, let's not use an electron, let's throw in a different particle.